of this integral is an measurable function on x. We note that we must choose one x in or space x, then compute this integral, this variable considered as an fixed element, okay? So that this is a function with respect other variable y, so that we take this integral with respect to y, the integral of f x y d nu y, and this integral is an scalar number, okay? So that this function is a function from x to r, okay? Now this function is an measurable function on x, and also this function y maps to this integral. In this integral, y considered as a fixed element, and this function is a function by this variable x, so that we take integral du mi x, and this integral is a scalar too, so that this function is a function from y to r, or 0 infinity, because f is non-negative, so that this integral is non-negative too. This function is tau measurable. This function is from y, by domain y. This function is tau measurable function, and in addition, we have these useful equalities. The integral of f on this space with respect to the product measure mu times nu equal these two integrals, integral on x, integral on y, this function, and by the converse order, integral of y, integral of x of this function, all of these are equal, okay? So that if we consider, for example, this function f from x times y to 0 infinity, and x s mu and y tau nu are sigma finite measure spaces. Okay, then we define two functions. For example, I denoted by h and k, these two functions. This is not that the function f may be at an infinity, so that we can write also f from x to this interval d mu y. We know that in this integral x is an fixed element, so we write, for example, by this notation. Okay, this cross section of f d mu y, so that this is the function by the variable y only. And also another function such as k from y to this interval, and this integral may be at an infinity. K of y equal to this integral on x, so that this y is a fixed element in this integral, so that this integral take with respect to other variable x, or we can write integral x, this cross section x d mu x. Okay, now by Tunnel's theorem we say that if f from x times y to this interval is S tensor to measurable, these two functions k and h are measurable too. Okay, Tunnel's theorem. F from this product to 0 infinity is by this sigma algebra measurable, then h is tau measurable, sorry, S measurable because h defined on x and the sigma algebra of X is S, so that we must write H is S measurable. And K is tau measurable. And also we have this useful inequality f of x and y d mu times mu with respect to this product measure and f as a function on this set equal to integral of x y f of x and y d mu y d mu x, and also equal to this integral. F of x and y d mu x d mu y. Okay, in the first integral, at first we must take the integral with respect to y and then with respect to x, and in the second integral, at the first we must take integral with respect to x and then we must take the integral of this function with respect to y. Okay, and by our notation is equal to the integral of h d mu, and this is equal to integral of y for k y d mu y. Okay, this is exactly our function h, and this is exactly our function k. Okay, if we define these two functions h and k, Tunel's theorem says that the integral of f with respect to this product measure equal to the integral of h with respect to mu, and also equal to the integral of k with respect to mu. Okay, dear students, do you have my voice and do you see image? Okay, thank you. Proposition have a straightforward proof, but its proof is almost lying, and proof is very straightforward and useful for you. Okay, but I omitted the proof of this because slightly is lying. Okay, so that please understand this proposition only. I omitted the proof of this for you. Okay, let me write for you. اوكي، أنا لا أطلب منك إثبات ذلك، فقط من فضلك تعلم وجها تماما. اوكي، do you understand it? Okay, okay. Ask. Let me review again the tunnel is new of finite major spaces, and suppose f from x times y to this interval is s tensor 2 measurable. Then this function is an s measurable function. We denoted this by h, for example. Okay, and this function is 2 measurable, and we have these equalities. The integral of f equal to these two integrals. Please note that in this section I remember that we have two major spaces, x, s, mu, and y, 2 mu, for example. And then product measure on this sigma algebra. We define all of these in previous session. Okay, now in Tunnel's theorem, for a function from this that is S tensor to measurable, we see the relation of the integral of f and with respect to this product measure, and integral of f with respect to two measures nu and mu. Okay, nu and mu. This integral takes with respect to nu and mu, but this integral take with respect this product measure. Okay, we have some example. Tunnel's theorem can fail without the hypothesis of sigma finite. For this, in the Tunnel's theorem, we assume that these two major spaces are sigma finite. Okay, If we omit this assumption, this theorem may be false. For this, suppose beta is the sigma algebra of Borel subset of this interval. Lambda is Lebesgue measure on this measurable space. This is our X, for example, and this is our sigma algebra S. Sigma algebra of all Borel subsets of this set. And mu is counting measure, so that we consider two measures. First, Lebesgue measure, second, counting measure. And let D denote the diagonal of this product space. D equal to X and X such that X belongs to 0, 1. This is a subset of this product space. And we consider this product measures 2, okay? Lambda times mu. This is Lebesgue measure and this is counting measure. Then we see that these integrals phi of D characteristic function on this set equal to, at first we must determine this integral, okay? And mu is counting measure. And this integral by counting measure equal to 1, because you must consider X as an fixed element. And then you must compute this integral. Please note that this is equal to 1. If mu is counting measure let me write by another color such as this. Okay, let mu be counting measure on 0, 1, and lambda be Lebesgue measure on 0, 1, okay? D equal to diagonal of this product space. X belong to 0, 1. Then the integral of phi of D x y d mu y, d mu by counting measure, okay? D mu y, d mu y equal to phi d of x and x only, and this is equal to 1, because this function only on this point equal to 1 and in other point equal to 0. It is not that if we consider this plan, for example, this or paradise space okay, and this is all diagonal. For example, this is also D, okay, D. Please note that in this integral x considered as a fixed element. For example, this is our x, okay, and this function by this variable is fixed, and this is our variable y. Only on this points x and x, this function equal to 1, and for each y non-equal to y x, this function equal to 0. By counting measure, this is equal to 1. This integral equal to 1. And so we have this is equal to the integral of 1 d lambda, and this integral equal to 1 by Lebesgue measure. This is Lebesgue measure and this is counting measure. But if we change the order of integration, we have this integral at the first integral with respect to Lebesgue measure, and integral of this function with respect to Lebesgue measure equal to 0, because this function only in one point equal to 1, okay, and otherwise equal to 0, only in one point equal to 1. The Lebesgue integral of this function equal to 0, so that this integral, this internal integral equal to 0, and this integral must be equal to 0 too. So we see that these two integral is not equal, and we don't have the Frobenius theorem. These two integrals are different, okay, and also as another negative if x this sigma j sigma k equal to sigma k sigma j, because this is one integral in counting measure and this is another integral in counting measure. Let's see its proof. Apply Tunnel's theorem to mu times mu, where mu is counting measure on z plus or integers. Okay, integers. So that if we consider okay, as another example, let x equal to y equal to natural numbers or z plus. Okay, mu equal to nu equal to counting measure. Then we know that any function f from x times y can be considered as a double index sequence, such as this. I is from 1 to the infinity, because f is a function from n times n to 0 infinity. Okay, if you consider xij as this for each I and j in n, if we denoted f of I and j by x by the index ij, we can write this function by this double index sequence. This is f of I and j. Okay, now by the Fubini's theorem, theorem, we see that the integral of f xy, or we can write ij, for example, okay, on a natural number d mu I d mu j equal to these integrals f I j, sorry, all of this equal to mu, counting measure, so that this mu is equal mu, and we have this again d mu j. d mu I, okay, but these two equal to, for example, the summation of x ij, or let me write by this notation again, d mu I, so this is I from 1 up to the infinity, okay, d mu j, and this summation f I j mu j, so that this is j from 1 up to the infinity, and d mu I. Please note that this is, for example, for inner integral equal to this summation, and this inner integral equal to this summation, and in the next step this is equal to this summation d mu j, j from 1 up to the infinity, then I from 1 up to the infinity, f of I and j by our notations we can write x ij, okay, and this is equal to sigma I from 1 up to the infinity, j from 1 up to the infinity, x I j, so that we have the nice example for non-negative double indexed real numbers, because in the Funer's theorem we consider a non-negative function, okay, so that this function also, this function f must be non-negative, and we denoted this by this sequence, okay. Okay. Dear students, do you understand? Mr. Carson, you want I repeat this proof? Mr. Gaston, do you understand or do you have any questions? Again, proof. Okay, let's see. I repeat the proof of for this example. For this example, double sums of non-negative numbers. If this is a doubly indexed collection of non-negative numbers, we want proof that we can change the order of summation. Okay, we can change the order of summation. This equality holds by Tuner's theorem if we consider x and y in Tuner's theorem equal to z plus or natural number. Mu and nu both equal to counting measure. Note that we have Tuner's theorem for space n times y. There we have no either x and y equal to n natural numbers, or by the notation of book z plus. Okay, and this mu and nu both equal to counting measure. Then this theorem changed to this useful example: x equal to y equal to natural number, mu and nu are counting measure. All of this counting measure. Then we know that any function from x times y equal to n times n. Okay, any function from this to 0 infinity can be write in this notation: f of I and j equal to xij. Okay. Now only we applied Fubini's theorem. Okay, by Fubini's theorem we have this equality. This is exactly Fubini's theorem. Okay, this integral equal to this integral. But this x and y are natural numbers, and this nu and mu are counting measures. Okay, this mu and nu are counting measure. Now we see that this internal integral equal to this summation by the definition of counting measure. We see that this example in the previous sessions. Okay, and then this integral with respect to j equal to the summation of this. Okay, and finally we write instead of this real number. This is a notation. Okay, and for this integral we have this method again. Do you understand, Mr. Gaston? Mr. Gaston, do you understand? Okay. And in the next we have Fubini's theorem. That is very important theorem. Suppose x is mu and y to nu are sigma finite major spaces, and suppose f from x times y to minus infinity plus infinity is S tensor to measurable. This function is measurable with respect to the sigma algebra again. And the integral of absolute value of f with respect to the measure is these two integrals are finite. This integral is finite for almost everywhere x, and this integral is finite for almost everywhere y. Okay? Furthermore, this function is measurable because we can define this as everywhere, almost everywhere. Okay? And also this is a real numbers for almost everywhere. These two functions are S measurable and to measurable respectively, and we have this equality to, please note that this is finite for almost everywhere, mean that mu of this set x belonging to x such that this integral be infinite. Okay, d mu y equal to infinity equal to 0. Mu of this set, the set of all x, such that this integral be infinite, not finite, must be equal to 0, and also other ones, mu of the set of all y in y, such that this integral f x y d mu x be infinite equal to 0 to this equal to this, and this equal to this. Okay, this is the definition of these sentences. So that this is a real numbers almost everywhere. When we can define this function is S measurable and other function is tau measurable, and we have this equality to. Let's see the proof of the Thuvenis theorem. By Thuvenis theorem we can prove this useful theorem. Thuvenis theorem applies to the non-negative function absolute value of f. Okay, because I mentioned that Thuvenis theorem is for non-negative functions, and this is a non-negative function. Thuvenis theorem implies that this function is S measurable function on x, hence the set of all x such that this is infinite must be belong to S. And Thuvenis theorem applies to this function, also tells us that this integral must be finite, because the iterated integral above equal to this, and we assume that this integral is finite. Okay, this integral is finite. by Tunnel's theorem, this integral equal to the iterated integral above. So that since this is finite, this must be finite too. The inequality above implies that mu of the set of all x such that this is infinite must be equal to 0, because otherwise this integral is equal to infinite. Okay. Now recall that f plus and f minus are non-negative S tensor to measurable function. We see this statement, okay, such that absolute value of f equal to the summation of f plus and f minus, and f equal to f plus minus f minus. Okay, see 3.17. Now applying Tunnel's theorem to f plus and f minus, we see that these two functions, because these two are non-negative, okay, and we can apply Tunnel's theorem are as measurable functions from x to 0 infinity, because f plus is less than or equal the absolute value of f, and f minus also. This set and this set have mu measure 0, because the set, please note that this set is a subset of this set. Please note that these two sets are subset of this set, the set of all x in x, such that integral of y absolute value of f, okay, d mu y equal to infinity. If we consider this set A, for example, this set B, and this set equal to C, then and B, for example, this integral equal to infinity. Now by this inequality, if this integral equal to infinity, this integral of this function equal to, so that it must equal to infinity and should be A. And also for this, if x belongs to C, this integral is infinity, so that this integral of this function equal to infinity, so that x must belong to A. Now, since mu of A equal to 0, by these three assumptions, we see that mu of B and mu of C equal to 0. Mu of A equal to 0. Please note that this is our set A. Okay, mu of this is equal to 0, so the of two set must be equal to 0. Thus the intersection of these two sets, which is the set of all x such that this integral is not defined, also has mu measure 0. Subtracting the second function in 5.33 from the first function in this, we see that function that we define to be 0 for those x where we encounter infinity minus infinity, a set of mu measures 0 as noted above, and that equal this elsewhere is an S measurable x, so that subtracting the second function from the first in this 5.30, this and this, okay, you must subtracting this and this, okay. The function that we define to be 0 where we encounter infinity minus infinity and equal to this elsewhere, so that this function equal to this. Please note that we have a function, for example, we can denote it h, okay, h of x equal to if we consider this as h1, for example, and this is denoted by h2. h1, h2, h1 of x minus h2 of x if h1 not equal infinity or h2 non-equal infinity, and otherwise we define 0, because in otherwise we have both of this must be infinity, sorry, so that this subtraction equal to infinity minus infinity, and this is ambiguous, okay. In these cases we define 0, and we see that the set of all x such that this be infinity and infinity have mu measure 0. But please note that this is equal to the integral of f. Integral of f, because this is integral of f plus minus integral of f minus. This is by our definition the integral of f. The new y on y and 0 in these two again. Okay, we must repeat this and otherwise. So that this function is measurable on x. Now we see that the integral of f on this product space and with respect to this product measure equal to the subtraction of these two integral, but by our definition of integrals we define this for arbitrary function f, the integral of f equal to the subtraction of f plus and f minus, integral of f plus and f minus, by this condition that these two integral not equal infinity in the same time. Okay, but this is equal to this by Fubini's theorem, because f plus is non-negative and this is equal to this, so that we can write this subtraction by this integral, and this is equal to the integral of f, because this is f. Okay, f plus minus f minus equal to f, and we have this equality, and similarly other inequality in Fubini's theorem can be proved. This integral also equal to other integral, so that we have this equality in Fubini's theorem, so that the base of the proof of Fubini's theorem is Tunel's theorem. Okay, is Tunel's theorem, and we can define this function and see this equality is whole again. Okay, dear students, it is enough for this session. We can continue in the next session. Do you have any questions? Dear students, do you have any questions? Okay, thank you very much. Thank you for your attention, and goodbye for now.